we can start. So in this session, we have the view of the NORCICS, it's the Norwegian Centre for Cybersecurity in Critical Sectors. So I will pass the floor to Vasilis Doulos, that will do the presentation and tell you more details about this center. Okay,
thank you, Theodore. Yeah, good morning, everyone. Nice to have you here and nice to welcome you to Norway. I hope you enjoyed. I hope you had a interesting, creative, and productive meeting. We had our own NORCICS meeting yesterday, and I hope you enjoyed dinner and hospitality. The weather is not optimal, I know, but it is what we have at this time of the year. I will tell you a few things. I'm Vasilis Doulos. I'm associate professor at NTNU and product portfolio manager for OT security in Telenor, representing the critical infrastructure security and resilience group. We have been partners at ELECTRON from the beginning, and for those of you involved at SD and Microsoft before that, we have it means that we have a longer relationship over the past 5-6 years. Not very active at the moment. Our tasks are mostly completed, and therefore we are a little bit more silent in the past couple of months within ELECTRON. I will tell you today a few words about NORCICS. As Theodore says, that's SFI means Center for Research-Based Innovation, and the center focuses on cybersecurity in critical sectors. A few facts about the center. It is the center is funded by the Norwegian Research Council. It's the only such center in Norway which has been funded and is focused explicitly on cybersecurity. We started about 4 years ago, and given that the duration is for 5 + 3 years, there is a near midterm evaluation of the center. We are actually right now going this midlife evaluation. The total budget of the center is about 215 million Norwegian kroner. I would translate that in euros, but that changes minute per minute. So that's the number. Half of it, approximately half of it, is provided by the Research Council of Norway, and the rest of it is provided by the partners who constitute the consortium. Talking about the partners, the coordinator of the center is NTNU, and there are 18 partners in total. 4 of them are research providers, and 14 are users representing industry, government, and other organizations. The center has a quite broad scope with respect to critical infrastructure security, but there are specific sectors which are in focus for the center. Primarily, that is energy, manufacturing, oil and gas, healthcare, police, process industry, and defense. The center, from its conception, is rooted on the Norwegian national strategy for cybersecurity on critical sectors. Probably cannot read it, it's a very short text, but the idea is to enhance preparedness of the Norwegian society and Norwegian actors in order to be able to respond and react to threats and attacks to critical infrastructure. And that means both by developing and deploying technology solution in that respect, as well as enhancing preparedness measures and awareness of operators and the citizens and the society at large. On that basis, we set up the objectives of the project. The vision of the project is quite straightforward. Norway, in its own right, in many aspects, is one of the most digitalized countries in the world. And that is reflected both on the public sector as well as on daily life. Norwegians and Norwegian organizations are very keen and very familiar with using technologies and digital solutions in their daily life and operations. And the vision of the center is to contribute to making Norway one of the most securely digitalized countries in the world. And our objectives map directly, the objectives of the center map directly to that national strategy in terms of establishing both through primary research and development, establishing solution processes and methods to enhance this preparedness and enhance the overall cybersecurity posture of Norwegian critical infrastructure and operators of critical infrastructure, but in addition to that, demonstrate the relevance and applicability of such solutions in real-life applications. This is to some extent the network. As I mentioned, there are quite a few partners. Most of them are coming from industry, and they are contributing to the operation of the center, both financially, of course, but also in terms of providing knowledge, experiences, solutions, as well as their own viewpoints in terms of what would constitute a feasible solution, both technically, operationally, and commercially to a great extent. And in addition to that, there is a quite broad network of international partners who support the operations of the systems, populated with external viewpoints, let's say, international drivers and knowledge about regulation, legislation, know-how. And they also constitute part of the quality assurance of the project, providing some degree of guidance in terms of the excellence processes which we run within the center. I would say I'm leading work package 5 in the center that has to do with communication, dissemination, knowledge transfer, and so on and so forth. That's my formal role. I'm also leading technical tasks related to digital twins, cyber ranges, primarily in energy and manufacturing. But through work package 5, I would say that this community is one of the key elements of NORCICS and one of the key contributions of NORCICS, bringing together people to discuss. Norway is a relatively small country in terms of this community, as it's in Europe. The OT specialists are quite a rare specimen. This applies also in Norway, and bringing them in the same room, either to have dedicated workshops on thematical areas, on specific verticals, socialize, to exchange ideas, to exchange priorities, share knowledge, visits, site visits and laboratory visits that can provide an understanding of the capabilities that we have in place in the country and how we can further utilize it in other activities. It's absolutely essential. And of course, within the center and through the center, we have established communities of interest. NESIOT is one of them, focusing primarily on IT and OT integration, bringing a closer group of people together to exchange ideas and thoughts about that. Similarly, there are other communities of interest in other focus areas of the center. NESIOT is one that I would say is more relevant to ELECTRON. In case you want to know more about that, Haptamu, if you may, is leading NESIOT, so feel free to reach out to him and exchange further ideas and thoughts about the operation of that community of interest. Now, as I said, this is, from my point of view, this is one of the key benefits of having such a center. And in that sense, bringing together people and exchanging ideas about best practices, know-how, technology solutions, and so on, allow us to perform our key task as a research innovation center or research-based innovation center, which is how to bridge the value of depth between TRL 4 and 6. We have very often universities and research institutes doing primary research up to laboratory demonstration or small-scale demonstrations. Of course, through Horizon projects, we go a little bit beyond that, but it's very common in our activities to focus down there. On the other end, we have operators, technology developers, and end users that are mostly focusing in higher TRLs from 7 and above. We have a lot of results coming in from projects like ELECTRON and other activities of the research group and the institutes involved that lead to higher TRLs, but this is very hard to communicate and integrate into actual operations within the businesses in the country. And bringing them together within such a center and allowing this cross-pollination and the exchange of ideas, communication of results is absolutely essential for securing the digital transformation that is occurring in the country. And in that sense, this is how we how we come up with and organize our research tasks. There are several research tasks within the center, focusing on specific themes, trying to resolve specific topics. And we follow a very industry-driven process on both establishing them and running them, with identifying problems and translating them into research activities or demonstration activities that run through the project lifecycle, all the way to validation and on-the-field validation of those results that are developed within NORCICS. A little bit more information about our research topics within the project. It's quite broad, starting from theoretical foundations, as well as more towards applied research. The application domains are critical infrastructure in general, but we have a particular focus on, as I said, energy sector, manufacturing, industrial control systems, Internet of Things, and so on, with specific sectorial domains. We use this cube from the taxonomy, cybersecurity taxonomy, to define where our work is, but I think you have got a good understanding of the broadness of the scope, as well as of the application domains within the project. This is our current structure, and this is how we operate the center. There are 3 supporting work packages focusing on project management, innovation-driven activities, and the one I lead on dissemination and knowledge transfer. And there are 3 core work packages that perform these research and innovation activities, starting with foundations, technology, application and service development, and the demonstration phase. This is a common structure. What we attempted to do, and it's working quite successfully, is to define specific focus areas, which were driven from our own partners, focusing on IT and OT integration, 5G, human and organizational aspects, and data analytics, and use these as a core, use the work packages as a core of operationalizing the center, but using these focus areas as the core of driving the research activities and driving the development of the community of practice, a community of interest within the center and the broader Norwegian community. And then, yes, the research, the specific research and the development tasks run across those verticals. It's a good way for us to keep track of it and keep our sanity, and it's also a very good way of us to identify gaps and synergies across our partners and across our overall activities. A little bit of the impact of the center, and as I come closer to the end of the presentation, overall there have been 12 PhDs hired within the center, and still are 4 are still to be hired. 5 postdocs, with 1 more coming, 2 researchers with 1 more coming. There have been totally 12 affiliated PhDs, and these are mostly industrial PhDs coming from our industrial partners, partially supported from our center, partially supported from Research Council and our industrial partners or other projects. There have been, I would think that now it's more than 40 master theses on topics within the center, more than 250 publications, and more than 30 spin-off projects from the center, half of them being nationally funded and half of them being Horizon, or not Horizon, within the European frameworks. The overall estimated economic impact so far of the center in the half-life is about 1 billion Norwegian kroner in terms of initiatives and activities performed. And that was it. I'll just close with what I said in that slide with a lot of pictures. We believe that collaboration is the foundation of innovation, and we try through this process and through those communities that operate within the center to drive innovation and research within cybersecurity. Thank you for your attention, and if you have any questions. No? Okay, well, I'll be around, so we can take that later. And we have 3 more presentations from NORCICS point of view.
Is the plan to continue after the last 3 years?
It is expected that the center will be self-sustained after that, through the spin-off projects and through the communities that it will keep going then. But that's the end of the external funding, let's say. We have 3 more presentations for you from NORCICS. There is one on a specific research topic that's very relevant to ELECTRON. There is one providing, again, research results, but more from the perspective of our partners, of our industrial partners, and that gives you an understanding of the applicability of the results and how the partners or actual problems drive our research. And there is also one presenting you available infrastructure and available resources, as well as results both from that were relevant both for SDN Microsense and ELECTRON, and how we use infrastructure in order to drive and support our research activities. Thank you very much and enjoy.
So thanks, Vasilis. I don't think we have any questions from the live audience. Let me check the agenda. So the next presentation is from Arne Rohr Nygaard. I hope I spelled it correctly. Let me find the correct file. Is it? Okay. Let me share. Not this one. Not this one. Sorry.
Ja,
Vi är osäkra på S, nu står det något sätt guy. Vet det.
presentation mode.
Sorry, can you repeat, Alon, can you repeat the question? Alon, can you hear us? You asked something, or you unmuted yourself in accident?
This one, yes.
Yes. Okay.
You want it in presentation mode or
Let's check it.
is this?
Which one?
No, this. Think? Yeah.
Yes.
Okay. Yeah. Very happy to be here. I'm working in the power company, the grid company who provide this area with the electricity. Suppose Hamar is about where you are here about now. So in this area, 2 million people live here. Not much maybe from where you come, but for Norway, that's a lot of people. In Norway, we are about 5 million people. Not a little city in Europe, but in this part of Norway, it's a very important part for Norway. A lot of industry and a lot of people. So I work in Elvia, the grid company, as a security advisor. But I also had the opportunity to take an industrial PhD. So I can do a PhD while I'm working. So the Research Council provides us with some of the funding, and I use 75% of my work for the PhD and 25% as a security advisor. So I have one leg in industry and one in academic. And so that's, I don't know if it's like that in Europe, but it's a very nice way to do a PhD. This is a heat map of the all the electrical grid in Norway. I often think about it. It's very like the human body. You see, the electrical grid is like the veins in the body. And if you lose some part, the rest is functionable. So we often use roads as an example, but I think we could use also the body as it's very similar to the electrical grid. Very important. And in the middle, we have these operation centers and the critical infrastructure, the cybersecurity part, and like viruses and infections. So I like to often to think about the electrical grid like the body. So Vasilis showed you NORCICS, but my research in kind of 3 areas is in the cyber-physical system, and I work with reverse engineering, hardware reverse engineering, and I also diving into this, the NIS2 regulation. How will the NIS2 regulation impact on the power sector, and especially the OT systems? If you read the NIS2 regulation, you can't find OT anywhere. It's not mentioned, but I think they have mentioned IT. I think we are in it, but there are really no OT mentioned in the regulations. But I suppose they have thought it was. But this is what happens in Norway. It happens, suppose, all over. That's digitalization. The electrical substation with a lot of wiring. No, only one fiber, and we use. So it's and this cyber physical systems. So and this in the electrical grid, we see all this digitalization of the substations, and a lot of SCADA systems, and even cloud systems. That's also challenging in the auto systems. So, but I'm worked a lot on this, on awareness, very much on this procurement in the supply chain, the third-party risk, and about compliance with the procurement law and regulation. So that has been my focus. And when I started, this is the idea when I started my PhD. This was the book that inspired me, the UAV challenges. And in these 4 years I have been researching, this challenge has been evolving. It's not only UAV, it's excuse me, Chinese products maybe. It's as Chinese in everything. And maybe that's a challenge. But so we see in Norway, we don't use UAV in critical infrastructure. We see in the US, they don't UAV. We are skeptical GI drones. We are Kaspersky, maybe the Russian product, maybe be banned in US. So there are attackers all over. So, and we have to cope with it because we have to use these products. We have to use them. And that's why I dived into how can we find the vulnerabilities? How can we be sure that the device is safe to use? And I've dived into the use of reverse engineering. So my PhD is how we can use, especially hardware reverse engineering, as a tool, a vulnerability tool. So, but overall, it's about this, the digital supply chain with vendors and vendors. It's like this. It's a lot of steps before you get a product. In design, the vendor suppliers, they put together a product with some functionality, but what's inside it? How can we be sure that it's safe for us to use? So that's been my issue. And it's not only mine, ENISA, supply chain, the #1 threat. So, and it's difficult. We trust our suppliers. We trust Microsoft. You know CrowdStrike? Everybody trusts CrowdStrike. It was a failure. But see what happened when there is a failure. It was not an attack, but it could have been. It's example for how we are very dependable on, and a lot of us, the same products. And if somebody does something, we saw the day before Ukraine war, the KSAT satellite system went down, compromised. It was already there, waiting, just click. So maybe there are in other things too. We don't know. So, and that's, IT is IT, but I'm more into OT system because in an IT system, you can maybe roll back a backup or something. In an OT system, you maybe kill somebody if what you see in your screen not is the same as out in the field. Somebody had tampered with it. All the switches are turned around. So you see there is no power. Okay, you say to people you can go work, and it's power. So OT systems, that's the real thing about IT and OT. OT is about the real world. It's what's happening in these physical processes. So that's why I'm very interested in OT systems. And I saw the Cocoon project here was very, very interesting. It's kind of the same topic then. And you see 0 days vulnerabilities. This is just, this is real. It's happening all the times. And that's why I'm working with this. How can we trust a device? And in the bottom of everything, there is some hardware. And in the hardware, you have software. We call it firmware. We at the lab, we do side channel analysis. We can open devices, take out the firmware. We can change the firmware, put it back. It is possible. We do it. So, and then we can do it. Someone else can do it. It's not. It's quite easy. We do side channel attacks on the chip to provide the passwords, and when we have the passwords, we can do whatever we want. It's doable. Absolutely. We have a lab at Gjøvik where we do this. We cooperate with a company in Netherlands, the Riscure. They are very good at hardware. They are about 300 hackers. You can send, if you are a vendor, you can send your products to Riscure and test it for you before you put it to market. But we have bought all our equipment from Riscure. So we have this equipment at Gjøvik just now for education, and we have a new master course coming up this fall. It's called Hardware Security and Embedded Systems. So it's a new course for students. So, and we have the lab. So we intend to build new knowledge. And this is also just an evidence this is happening. This hardware vulnerabilities is, and very much because I said it's a Chinese in everything, because this is costly products. When you buy something, a chip, it's made for a lot of things. And in your product, you maybe use something. What is all the other things? You don't know, because they put the same chip in a lot of things. So, but this is kind of difficult thing. So this hardware reverse engineering, you see, this is just a kind of understanding what's inside and some techniques to do it. But for critical infrastructure, it's very important. I knew the armed forces do this kind of things, and you can hire companies, kind of certificate your components. But yeah, we first want to raise the knowledge level and the skills. So if the dream is to make a lab that we can do business, but we will wait and see. But my PhD I put in this third part management. I put in reverse engineering as a tool, a technique to check things. And we have made some. I've been down in Athens at the University of Piraeus working together. We have worked on a paper. So this is the one is to trust a supplier, and to have models and risk assessment methods to do on the supplier before you do the procurement process. Then you are hiring something. You can go through a checklist on the supplier and see reputation, whatever. And then you can trust how to trust a device. And we have seen how you can put these things into the procurement and the contractual clauses because you have to start early. You can't, when you buy something, it's very difficult to come to the vendor and say, I want to check it, it's too late. So we have to do it very, very early. So that's my work, so to say, and I put in all my publications. I'm almost finished. This is the draft of my PhD thesis. So in some months, I have the dissertation, I hope. So my supervisor is Socrates Katsikas. I suppose you know him. So it's been a very nice journey. So this is where I'm in a few months. I hope I'm I have it. But I have puzzled it together all the 4 years and sent the first draft to my supervisor. So waiting and see. Okay, thank you.
Lab,
Yeah.
the certificate. Is there, let's say, the business plan is eventually to provide certification for hardware?
First, we have to do at the university.
Yes.
But as a spin-off, or that's a dream. But they have done it in Budapest, in the trust. They are all universities. It has started at the university, and you can take it out to do business. But that's some years.
Are you following something specific with respect to certification or
No,
regulation?
we
at
are
this
just
point?
in the start. We have to learn, have to have the methods. We have to, explore these things. So first is knowledge, this course, and spread the knowledge to other students. And maybe it can be some business, but I don't know. Search Lab is in Budapest. They do same. They started at the university, and some of the guys took it out, but they collaborate with the university and do so. It's very nice. So I don't know.
Thank you.
I don't know if someone has any.
Go ahead.
One question, does Norway have to adopt the European regulations like NIS2 directive? Or was the process?
This is a pro. You said the GDPR we have to adopt because that was a directive. Is that right?
Yeah.
But the NIS2 is a lower. So Norway is an US member, and it's like a political process. The NIS1 come in 2016. In December last year, they adopted NIS1
Okay.
because they had the is it relevant? But now I think NIS2 is relevant. So they have made a new law in Norway that is called the Digital Sikkerhetslov, digital security law. But we are waiting. We don't know, but I suppose we will adopt it and then put it into Norwegian laws. So the power sector has their own laws. So in some way, I think we have to adopt it. And if we collaborate with Europe, so every vendor who wants to buy something or sell something to Europe has to talk to NIS2. So of course it will be, but I'm not sure how it will come. But everyone who collaborates with Europe has to copy. And like the Cyber Resilience Act is very nice. I like it because then the vendors have to tell more of what they do. And like this software bill of materials or a harder bill of materials even. So there is hope to So I like the new regulation really because we need it. So
Thank you.
Okay, I don't know if someone else has any questions or from the online audience. Okay, thank you once more. Very interesting presentation. And then we move to the second presentation. It's from Jessica, how you spell it, Helwani. I hope I spell it correctly. Let's find the presentation. Oh, this one. Okay, let's try to save it. This one.
So, good morning, everyone. My name is Jessica. I'm from Brazil. and I'm part of NORCICS, as Vasilis introduced it. I'll talk a little bit about patch management digital twin for energy systems. And here's a brief agenda. I will start introducing the project members and also contextualizing the project. Then give you an overview of this patch management digital twin and explore the next step, which applying the Delft methods, whereas there is room for collaboration. So it's the main reason for being here. And also, as Vasilis said, there are several possible collaborations within ELECTRON. So introducing myself, before the PhD, I was working in industry. I've worked 6 years at White, so I come from the energy sector, and then 1.5 years at Siemens Infrastructure. And then I was in direct contact with end customers, so I could hear some challenge, and it was a motivation to do the PhD and start specializing more in cybersecurity, because I could see how the regulations were impacting and how it's hard for them to comply with the new regulations. So the overall goal of this presentation is both present the results of the project so far and also try to get some collaboration for the Delft methods. And usually I don't talk so much about myself. I'm just doing so because, as I said, you probably receive emails. So I'm a real person. I'm not trying any social engineering. And if I contact you, it will be either from one of these projects or the project members. So Vasilis is my main supervisor, and Socrates and Sivi are my co-supervisors. So all the contacts I try for the Delft methods will come from one of them or the projects. And contextualizing the project, I'm part of NORCICS, Step 2.3, and I was hired through the PERSEUS doctoral program, where it's mandatory to have either an academic or industrial internship. So, as I said, I come from the energy sector, then I chose the industrial internship, which I did at Siemens Energy. So what I'll talk about now, that is more related to the research, is an overview of this proposal of a patch management digital twin, and it was developed in collaboration with Siemens Energy, where I had a 2-month internship. And here are the main results. So just to, I know that there should be lots of partners from the energy sector here today, and the way that this project relates to energy systems is through this typical automation architecture. So these are the elements that will appear in the patch management digital twin. And also one of the goals is to get real components. As you can see here, I'm just saying PLC, but there is no brand, no model. But the idea is to make this as specific as possible for the next step to get real security notifications. And a high level of the research, what can be seen here. I tried to make it more visual with a puzzle, because that's really what we did. We got some relevant regulation. So we are following IC 62443 for patch management. And for the digital twin framework, an ISO standard. Actually, a comment here, I don't know how many of you are familiar with digital twin, but it's a lot of misconception about the term, and it was one of the challenges when I was doing the literature review. So I'm following this definition from the standard and also the framework to apply this for patch management. And CVS status score were utilized for patch prioritization and to organize all the data that we got from this application of the standards. We are using another IC standard for asset administration shell. And as you can see here from the definition of this standard, the digital twin, it fits for a purpose digital representation. I highlighted purpose because many times it's only related to simulation, and we think that we should mimic all aspects of the real system, but it might depend on the purpose, and then the layers that we are mimicking vary depending on the purpose. So that's why I highlighted this here, and we were focusing in this case for patch management. Giving an overview of the patch management workflow. So when I started the internship at Siemens Energy, they were already looking into vulnerability management in general as a broader topic. And wanting to know what data can be collected from your systems in order to have this vulnerability management. So we decided to follow IC, which is a very relevant standard in Europe. And as you can see, it starts from information gathering, then goes to monitoring evaluation, patch testing, deployments, and finally verification and reports. It's not mandatory, it's a guideline, but again, the information gathering also, it depends a lot on the purpose. So there are lots of information available in real systems, and depending on the functionalities that we want to apply and how much we want to mimic, this also might change. Now exploring the digital twin framework, the definition doesn't show all the layers. So this ISO standard, they show the digital twin as a combination of the several entities. The idea is not that you are able to read, of course, it's small, but my idea here is to show how the pieces of the puzzles and the standards I showed before, they match to form this framework. So what's in yellow here is customization of the standard for digital twin framework. And here it's customized for patch management only. So as you can see, there is the user interface layer they call as entity in the standard, and then other entities for the digital twin. In this case, it would be for software and hardware, and then the communication with the standard system. And again, as I said from the architecture, this would be the observable manufacturing elements. So besides this huge framework, according to these standards, to call something a digital twin, we would need to have all these entities and sub-entities. As you can see, it's very complex with lots of functionalities. And during the internship, we were focusing mainly on the collection, data collection part. So what data needs to be collected for the purpose of patch management? As the main result of the internship, we got the suggestion for what data can be collected for each of the phases according to IC 62443. And doesn't make sense now to go through all these tables. It's available in the paper. But what I wanted to show is how this can be utilized in an end user way. So this is just a mock-up of a possible platform for patch management, where you start seeing how the puzzles fit and can become a tool. So for example, if we have the same automation architecture that I started the presentation with, but here there would be a live system to show the priorities of the patches. And then one of the possibilities is not using the CVSS as direct comes from the public database, but there could be a different project, CIA, for confidentiality, integrity, and availability, for example. And then it could be possible to calculate different environmental score that takes into consideration characteristics that are unique to the system. And this could also be made in an asset-based way. So if we are going, for example, to look asset by asset, we would need much more data for each of them. So this menu is showing that you would have to know the communication capabilities, similarity with other assets. So there are several other information that, as I said before, if we think about digital twin, depending on the functionalities that would be applied in this possible platform, there would be different data to be collected from the real systems. And then in an asset-based methodology, we would need much more to be able to calculate the environmental scores of the CVSS framework, for example, and then apply mitigations for each of the security notifications. This would be another example of other functionality, which is about the testing. So again, I know how important is security. I'm also specializing in this, but it's not the core business of energy systems. And then thinking about this and also take from my background in the energy sector, I know that budget limitations and resources are a great deal for energy actors. And if someone is following the IC approach and trying to have the testing environments, it's not really feasible to consider that it is possible to have the complete mirror of the real system. because it's usually very expensive. So again, some of the data collection suggestions that are in the tables are translated here. So for example, you can see redundancy, similar functionalities, if a device doesn't require plant interruption, or if the patches are approved by the supplier. So another example would be HMIs. I don't know how familiar you are with OT systems, but HMIs are usually not essential to the systems that are operating. They are usually utilized in emergency modes. So it would be possible if, for example, there would be an algorithm, and that's where the next step of the research is. We are thinking about developing these reasonings to allow, okay, if I consider that I have 3 generating units, for example, if it's a power plant, and then there are 3 different HMIs, but they have the same software, the same hardware, and it's not essential, and it doesn't require plant interruption if you update software or firmware. So this algorithm behind it suggests that there is no need for the testing environments. You could use the real system as the testing environments already. And another example would be for more essential devices like PLC, where the logic is running and you can't really stop. So even if the system is redundant, it might be risky to do something while the system is running. So the reasoning behind this, the algorithm could suggest that the testing environments might consist of a real PLC, real ID, in order to do the testing. But still, you'd have from the whole architecture just the need for much smaller sets of real devices. And you might be asking yourselves why not considering everything digital. But during my internship, I was talking with several people at Siemens, and we started going deeper. It's also related with what Arne was saying before. Many things are related to the hardware, and buffer overflow is a very common cause of these security notifications. So these kind of issues would be very hard to mimic in a simulation. So that's why this possible algorithm would suggest to have a real device with the simulating of the not of the whole behavior of the system, but focusing on these devices. And then the next step is to develop these algorithms. What I have been saying so far is an idea. As I said, the main result was the suggestion of the data collection, and then this is an idea of how this could be useful as a tool for patch management. So the Delphi method would be for these reasonings and algorithms. And here are some of the possible companies that we might collaborate with. So for the ones that are not familiar, the Delphi method consists of having a group of experts where we would have these rounds and try to achieve a consensus. I showed you some of the data collection suggestions and how they could impact these algorithms, but of course that it would be much better to listen from who is actually doing the patch management in power plants, substations, or transmission units. So each round consists of this preparing, conducting, and analyzing. Specifically for this case, the collaboration would consist of these rounds. So if you are from one of these companies of the ELECTRON projects and you're interested, this would be the rounds first starting with a consent that there would be gathering of some personal data, such as the role, email information, and commitment to participate of the forums. But then all the other rounds would be done through anonymous forms, so any company would feel exposed. And there would be a short video in between the rounds so that we can show you the main results and try to make it step more clear and how it's being applied in the project. And also here, I just put feedback, and this is a draft of the collaboration. I'm still in the preparation phase. But of course, that's the feedback can be done not only through the meetings. I just chose this template to be easier for everyone who is willing to participate, but we could also have meetings in between if any of you are available and would like to do so. Here is an estimate of time investments and benefits of this possible collaboration. So it would be around 2.5 to 6 hours. As I said, the first meeting and the videos would be mandatory so that we are all on the same page. But then the possibility of a panel discussion before the last rounds would be optional. But it's a very nice way of getting synchronous and real-time collaboration. And the benefits would be access to reports that will be produced after each round and room to be heard. I imagine that as partners of research projects, maybe you are willing to participate, and there was an interest in the beginning, so it's a way to have this contact with PhDs and more researchers working in the tasks. Also getting insights for internal circuits on patch management. So the idea here is not to say how this relates to regulations, but of course that patch management is one of the topics of any cybersecurity regulation. So at the same time that I will get insights from my research, maybe it also can be helpful for the companies to have ideas and insights on how to comply and how to optimize resources when doing the cybersecurity tasks that are, again, not the core business. And also just an idea of having an online board or blog updating weekly or bi-weekly the project results, providing room for collaboration also between partners, not only between me and the partners. So thank you, that's from my side, and I'm open to hear comments or questions, and also if you have any suggestions for tools to help in this collaboration, I'm open to hear. Thank you.
Participation is open to both academia and industries in this Delphi approach.
We are looking for energy actors, so it could be distribution, transmission, or producers, but we will try to get information on what criteria can be helpful for the ones who are really trying to apply some patch management methodology, so that we can have this criteria for the algorithms.
Any more questions? Okay, thanks again for your presentation. Let me check if you have something from the online audience. We have any questions? No. Okay, so we continue with the last presentation. We have Tesfaye, if I pronounce it correctly. Sorry if I. Let me find the presentation here. Is it?
Yes.
Okay, let me share the screen. So. Okay.
Yeah, thank you.
Yes.
Hello. I hope you can hear me at the back. My name is, okay, I will try to be more loud. My name is Tesfaye, from a researcher from Syntep Energy. I'll try to present you about the demonstrator activities we have in NORCICS, specifically focusing on the demonstrator activities we have in the energy sector, the future cyber physical electricity system. So I will try to first briefly present the background and followed by a list of demonstrators we have developed so far. And lastly, I'll try to give an overview of the different research facilities we have to run these demos. So in NORCICS, we have this work package 4 that focuses on demonstrator activities. The work package aims to test and demonstrate models, methods, and technologies developed inside the project. So we basically have input from different research activities of the project. methods, models, technologies, and we try to test them in a realistic environment, in a laboratory environment for validation and verification. Demonstrators are being developed for these 4 different sectors, but in today's presentation, I will try to focus on the demonstrators we have for the energy sector, the cyber physical electricity system. So why do we have this demonstrator? What is the objective? The first objective is to investigate how will cybersecurity technologies and solutions work for different applications, in this case, the smart grid applications. And the results will be used as a feedback to improve the developed methods and models. And if we get promising results, they will be used as a basis for finding the best practice for cybersecurity solutions. And combining the results from different demonstrators, it is possible to also make some guidelines and recommendations for cybersecurity solutions in the smart grid context. So let's zoom into the demonstrators we have been developing in the energy sector. So first, again, a brief background about the smart grid ecosystem. As most of you know, the power grid is under a significant transition, and there are different reasons for it. For example, we have this green shift that introduces a lot of renewable energy resources like the solar panels, the wind turbines into the grid, which results in some uncertainty in the operation of the grid. Nowadays, we have many new intelligent devices being introduced into the grid for automation of some of the operations of the grid. We have new loads such as EVs that not only consume energy, but also they can be used as a storage device, or they may put energy back to the grid. So the operation of the grid is becoming more complex. And in order to manage this complexity, we are using more and more ICT. And the challenge with the use of more ICT is that we are going to have new vulnerability, new risk from these newly introduced ICT support systems. And it is important to investigate the reliability, performance, and security aspects, considering the interaction between ICT and the underlying power system. So we are putting more and more ICT, and the power grid is becoming a complex cyber physical system. And what can happen to this ICT system? In NORCICS, we are trying to identify and develop different scenarios. The first demonstrator or use case looks into the use of new technologies for different smart grid applications, how these new technologies such as 5G performs in their use for some smart grid application. So we develop use cases that look into characterization, verification, and validation of new technologies such as 5G. There can be a failure on these newly introduced ICT components. We have use cases that look into this component failure, such as the hardware security of IEDs. There can be a failure on the communication system, or the communication protocols may have some vulnerability. And we have also use cases that look into the human factor. What if the operator misuses some of the ICT support systems in the control room? How will this affect the operation of the grid? So we have also demonstrated that looks into the socio-technical cyber resilience. An attacker may infiltrate the communication system, and it may result in, for example, a total blackout. So we have demonstrators that look into the cyber attack, the impact of the cyber attacks, and also test the performance of intrusion detection methods. So these are the demonstrators we have developed so far. We have 5 main demonstrators: hardware security of IDs, cybersecurity in 5G-enabled smart grid applications, cybersecurity in IEC 61850 protocol, which is one of the most commonly used protocol for substation automation, intrusion detection and prevention, and lastly, the socio-technical cyber resilience that looks into the human factor. So let's look into each of the demonstrators briefly, one by one. The first demonstrator is on hardware security. This demonstrator aims to investigate hardware security vulnerabilities of IDs. IDs are basically advanced control devices that are used for automation of the grid. And it also tries to analyze their impact on the operation of the grid. And if possible, it also aims to propose a countermeasures. We have these three NORCICS partners that involved in this demonstrator, Syntef Energy, Elvia, and NTNU. We use the reverse engineering laboratory to identify these hardware security vulnerabilities. There can be many types of hardware vulnerabilities of these IEDs, and there can be multiple types of hardware security attacks. But for this first phase of the demonstrator, we are considering this hardware security assessment through voltage glitching. So it's a hardware attack using this voltage glitching technique. This demonstrator has two phases. The first phase will be in the reverse engineering laboratory to identify this vulnerability. And later, once this is done, the IED will be moved to the National Smart Grid Laboratory in Trondheim for impact analysis. We will put the IED into a larger setup, and we will try to investigate the impact of this compromised IED on the operation of the grid. And in the reverse engineering laboratory side, all the necessary equipments are acquired. We have now the hardware IED, all the necessary testing equipments, and we have also prepared a simple setup to run this first test. And this is the setup we have in the GeoVic, the reverse engineering laboratory for the first test. As you can see, it's a very simple setup. We have this goose ping pong setup where we use a Linux machine with some Liva IC61850 library to generate a goose ping message. And this will be consumed by the hardware IED. And the hardware IED, upon receiving this goose message, it will generate another goose pong message. So here the aim is to just have a normal input-output operation on the IED side so that the researchers in the reverse engineering laboratory can play with it, and we know how a normal traffic should behave. So it is possible to identify if the hardware security attack affects the normal operation of the grid. So once we identify the hardware vulnerability, we will move the IED into a larger setup in the National Smart Grid Laboratory for impact analysis. So the setup for the first run is ready, and we are currently trying to have a discussion with the vendor before we start running the demo. And the second demonstrator is about cybersecurity in 5G-enabled smart grid applications. Here, the aim is to investigate the cybersecurity of 5G networks, considering these two different scenarios. The first scenario is the use of 5G for critical smart grid applications like protection functions. Here, we do have a very stringent time delay requirement. And the second scenario is the use of 5G for less critical applications like the demand response and flexibility resource activation, which has a relatively lesser time delay requirement. So we basically have two deployment scenarios here. For the critical smart grid application, we are considering to use private 5G because we have a very strict requirements. And for the less critical application, we are considering the use of public 5G networks with access to the internet. Yeah, and as you can see here, for the critical application scenario, we are considering different types of cyber attacks, such as smart jamming, whereas for the less critical application, we are considering attacks such as DDoS, the distributed denial of service, from behind the internet. And the laboratory setup to run this demo is also prepared. We have integrated the National Smart Grid Laboratory in Trondheim with the private 5G network from NTNU. And we did also some preliminary tests. We have put some antennas, gateways, picosets in the Smart Grid Laboratory, and we have made some tests. And this year we had also two master theses that use this test bench. The students look into this use of private 5G network for the critical application, specifically differential protection. The first student looked into the configuration of private 5G networks for differential protection in smart grid. So in differential protection, we have these two protection IDs that needs to talk with each other. They need to send a measurement between each other, the current measurement. And for this, we use the IEC 61850 sample value protocol. And these sample values are transported over a private 5G network. And the student was trying to configure the private 5G network to have a tailored system and to improve the performance of the 5G to transport these sample values. And the other student used more or less the same setup, but from the cybersecurity aspect, a DOS attack on the gateways is used and is applied, and the student tried to investigate the impact on the operation of the protection devices. And we had also this other work this year, a publication that looks into the use of private 5G for communication-assisted distance protection. It's more or less the same setup, but in this case, we don't have measurements. We have the control signals that needs to be sent between two different substations that are far apart. And for this, we use the IEC 61850 goose message. And we have got quite a good promising results from this private 5G network. And we are currently trying to define more cybersecurity related use cases like the scenarios I showed you in the previous slide. And the third demonstrator is about intrusion detection and prevention systems. Here, the aim is to investigate or test new methods to detect cyber attacks, malicious packets in digital substations. We have these three partners that work on this demonstrator. Here, we use a test bench system developed under another EU project, ERIGRID. And we have also actually used this test bench to validate a tool developed by one of the ELECTRON project partner, Atos, now Evident. So they come in the lab and test their intrusion detection method. It's a model reference grid based on SIGRE test network. It models small metropolitan area power grid network with 3-4 primary substations. And the test bed in the lab is a hardware in the loop setup where we can do high TRL level tests like TRL level 6. It's a hardware in the loop setup. So part of the system is modeled using real hardware IDs, RTUs, and SCADA system with industry grade switches for the substation communication. And part of the system is emulated using a real-time simulator, OPAL-RT. And as I said, the aim here is to use this test bench to test and validate intrusion detection and prevention methods developed inside the project. We are currently testing a machine learning-based intrusion detection method developed by one of NORCICS partner, NR. And we are also now trying to extend the test bed with new Cisco switches. We have started collaboration with Cisco, and they are providing us switches and also some software for deep packet inspection. So we are also extending the test bench system. There is also a plan to integrate it with CyberRange at NTNU Jovic to enable us for further test and experiment of new methods, intrusion detection methods developed by partners. And the fourth demonstrator is on cybersecurity in IEC 61850 protocol. This is one of the most commonly used protocol in substation automation. And this protocol has some weakness. For example, devices using this protocol, if they lose synchronization, the protocol doesn't have a mechanism to identify this loss of synchronization and reestablish it. And researchers from NTNU, James, has developed a mathematical model. And we have also now the algorithm written in C code And we're trying to prepare a laboratory setup to test and validate this algorithm developed by the researcher from Work Package 2 in NORCICS. And the fifth demonstrator is on socio-technical cyber resilience that looks into the human factor. Here, the aim is to investigate if operators can handle unexpected safety critical events and to find out if there is a way to improve the socio-technical resilience of the system and its organization. For this demonstrator, we are going to use a tool developed by Syntef Digital, a NORCICS partner. It's called Torque. It's a tool that can be used to provide challenge for the participants or operators in this case. It kind of defines the procedure to give more challenge, step by step, give challenge to the operators, define or guide the process, document the process, and also document the actions of the operators. And it will automatically generate a report that can be used for further analysis. And we have been discussing this with grid operator Elvia, a NORCICS partner, and potential list of use cases are also identified. And soon we will have a more technical discussion with Elvia to design the game. And the plan is to run this demo early next year. So this is the laboratory infrastructure, the research facilities we use to run these demos. At the center is the National Smart Grid Laboratory in Trondheim. We have integrated this laboratory with the private 5G network from NTNU. We have also access to commercial 5G network from one of the biggest telecom service providers in Norway, Telenor. And we have also connection to Cyber Range Lab at NTNU Jovik. A brief overview of the core lab infrastructures. The National Smart Grid Laboratory is located in Trondheim, and it kind of comprises different components, hardware and software to model a power grid as a cyber physical system. We have basically components in every layer of the cyber physical system. On the process level, on the power system level, we have generation, transmission, distribution equipments, including power electronics, converter inverters. And on the communication layer, we have industry-grade switches, routers, remote terminal units, hardware IEDs from different vendors, Siemens, ABB, Schneider, PMUs, merging units. And it also supports more or less all the most commonly used protocols, IEC 61850, IEC 104, the SCADA protocol, the MP3, the C37 PME protocol, or PCUA Modubus. And on the control layer, we have also a mini SCADA software, softwares like PDC to collect PME information. And all these devices are hardware. We have also a real-time simulator or PAL-RT to model and emulate the power system, including virtual IEDs. When it comes to 5G, we mainly use the private 5G network, an operational network from NTNU. It's a self-owned private 5G vendor managed from Nokia, and it's a standalone, so it's 5G core. And we do have also access to a commercial 5G network from Telenor, but it's non-standalone. The core part is 4G. The advantage with the private 5G is that we can change or manipulate, play with the configuration of the 5G network, customize it for smart grid applications. There is some limitation, so it's like a gray box for us, whereas the commercial 5G is a black box. We don't have any access to the configuration, but still it's interesting to do some research with public 5G networks to see if commercial 5G networks can be used for some smart grid applications. We have also access to 5G emulators, open source 5G emulators from Syntef Digital and NTNU. And this gives us more flexibility. We can change more configuration parameters inside the 5G core or radio. So in summary, we have these different laboratory facilities, and we mainly develop 5. So far, we have developed 5 demonstrators. And some of these demonstrators have multiple test cases. And this figure shows the mapping of the demonstrators into the laboratory infrastructure. And as you can see, we have at least one demo between every lab's smart grid at the center. And we have basically at least 5 different demonstrators running. Yeah, that's all I have. A brief overview of the different demonstrators we have developed so far. Question, maybe?
Thanks for the presentation. I don't know if you have any common question from the audience here or check the online. Yeah. Check here. Oh, I don't see any questions. Thanks again once more. I would like to thank again Vasilis and NTNU for organizing this event and for the hosting here. So we will have a break for lunch, and we will get back at 12:30. So thank you all. See you
1:30.
1:30. Sorry.